So the essential question today is how can we use the equation for acceleration to predict the motion of objects? So if I give you the equation for acceleration, can you use that equation to figure out what's going on? So here's the equation for acceleration. You may have seen this already on some of the worksheets we have. A average, sometimes we just write an A on this because we'll never be dealing in a case in this class where we have changing acceleration. We're always going to have the same constant acceleration. But in any case, A average equals delta V over delta T. So we know how to build an equation. So if we're given an equation, we got to be able to figure out what are the mathematical relationships that are shown in that equation. How can we break that equation down? So please take a second and see if you can write in your notebooks based on that equation. There is a blank relationship between blank, and then again for the second mathematical relationship that's shown. So if you did this, you should have realized that there is a linear relationship between average acceleration and change in velocity, because change in velocity is on the numerator or the top of that fraction. That shows it's linear with the dependent variable on the other side. And we should have realized that there was an inverse relationship between average acceleration and delta t, because delta t is on the denominator of that fraction, showing an inverse relationship. So hopefully you were able to take that equation and break it into the relationships. So before we're ready to use the equation, we need to think really deeply about what the math operators shown in this equation mean. We mentioned briefly that the average acceleration won't really come into play because all of our objects are going to have a constant acceleration, so the average is the same as the initial and the final. But the deltas in that equation are going to be really relevant, especially for the velocity, because our previous equation was v average, and this is delta v. So let's think about a moving object. Are v average and delta v going to be the same for that object? For almost every object in the universe, v average and delta v are different values, which means it's really important that you use the right one in the right equation or you will get the wrong answer. So a car moving at 60 miles an hour on the highway, its v average is 60 because it's cruising along, but the delta v is actually 0 because the velocity isn't changing. Think about any object speeding up, slowing down, whatever is happening. In almost 0% of the cases, almost zero, the delta V and the V average will be different values. Maybe a better challenge is, can you come up with an example of when they are the same value? If you can, come talk to me and I'll give you a little sticker or something as a reward. So in any case, you got to make sure that you're doing the right thing. Delta means change, so we got to calculate the change in velocity compared to the other equation where we were concerned not about how much the velocity was changing, but just what is the average velocity over the time. So you can ask yourself this question: which has more acceleration, a car that's going a constant 60 miles per hour on the highway for 5 seconds, or a snail that starts at rest and speeds up to 0.01 meters per second during the same 5 seconds? Maybe take a pause for a second and think about this. So as we mentioned a minute or two ago, if we're going at a constant speed at 60 miles per hour on the highway, my delta V is actually 0, which means that car has 0 acceleration, even though it's moving really fast. On the other hand, the snail has a delta V of 0.01 meters every second because it's speeding up from rest, which means that the snail, even though it's so much slower than the car, actually has more acceleration than the car because its speed is changing more. And that's why it's so important to pay attention to the math operators. Because most people, if you asked who has more acceleration, a car or a snail, they're going to say the snail for sure, or sorry, the car for sure. But there are cases where the car can have no acceleration and the snail might be accelerating more. One of the tools we're going to be using to sort of visualize the motion of an object is a motion dot diagram. So imagine you had a car that was driving on the highway, but it was dripping oil, like 1 drip every second as it was driving. What would those oil drops look like if the car was moving at a constant velocity to the right? So maybe in the space below this, you can sketch out what would it look like if we were moving at a constant velocity to the right. There's 2 things in your drawing. You should include an arrow to show which way we're moving, because you can't tell from the oil drips necessarily which way the car was moving. And the second thing we would see here is that those oil drips would be evenly spaced. If we're at a constant velocity, that means every second we're covering the same amount of distance, so my oil drops would be evenly spaced. So please take a moment to ponder, what does this mean about the car's acceleration during this time, and be able to explain why. If we're moving at a constant velocity, that means my delta V, or my change in velocity, is 0. So this car actually has an acceleration of 0 as it is moving. And we can tell that because we're covering the same amount of distance every second. Therefore, my velocity is constant and not changing. So another question, what would this oil dot drying look like if, instead of moving at a constant velocity, we're still moving to the right, but now we're speeding up gradually? Can you draw a dot diagram showing what that would look like? Okay, hopefully you drew your arrow to the right again, and this time you showed that the dot spacing is changing, right? As we're speeding up, the faster we go, the further apart those dots are going to be. So we see in this dot diagram that we were moving slow at the beginning and faster at the end. Is this a small or a large acceleration, and how can you tell? Take a second to ponder. So I would describe this as a small acceleration because the distance between the dots is not changing very much from dot to dot. We're getting bigger distance, but sort of gradually. So how dramatically the dots change in distance is going to be the indicator of whether we're talking about a large or a small acceleration. So given that, what would this look how would this diagram look different if we had a big acceleration? What would that look like? And it's going to be similar where the spacing is changing, but this time the distance between the dots changes dramatically between each dot. So right on the same screen, I only have like 6 dots, whereas I have 8 or 9 on the one above. So this shows that the distance is changing more and more each second, therefore the velocity must be changing more and more each second as well. You also should be able to answer conceptual questions about how changing one of these variables affects the other, now that we understand sort of why the math operators are important and the two relationships that are in there. So if you have two objects and one of them has a larger value of delta V in the same amount of time, what will that mean about the acceleration? So I have two cars, and one of them changes from 0 to 30 and the other one changes from 0 to 60, both over 2 seconds. Which one's going to have a higher acceleration? And you should be able to tell me, by how much does one have a higher acceleration and why? In the example I just gave, the second car is changing velocity twice as much as the first. Therefore, it's going to have twice as much acceleration because there is a linear relationship between average acceleration and velocity. Can you think of another example from your life of two objects that might change velocity a different amount in the same amount of time? And what could you say about the acceleration of those objects given that? On the flip side, what if we have two objects that are both changing speed by the same amount, but one of them changes speed in more time than the other? So this was kind of the example I gave when we originally introduced acceleration. I have two cars that are both starting at the entrance ramp of a highway, but one of them takes 3 times as much time to get up to highway speed. The other one does it in 1/3 as much time. What's true about the acceleration? And by how much? So if my crappy car takes 3 times longer to get up to highway speed, that's going to mean its acceleration is 1/3 as much as the good car, because there is an inverse relationship between delta t and acceleration. Maybe you can pause for a second and think about a non-car related example where you have two things that might achieve the same final velocity, but in different amounts of time, indicating that they have different accelerations. Okay, we have reached the end of this video. Please take a second, please, and revisit the essential question, which is, how can we use the equation for acceleration to explain or predict the motion of objects? Thanks for watching.